1.
Today we will study about the energy band theory in electronics. But first things first, we'll study some things. One of them is the wave function, which is a part of quantum mechanics. Wave function is represented by psi. The wave function tells us about finding the electron in an atom. It tells us about how much probable it is that the electron is found in a certain place. This is denoted by the wave function. This is the first thing you need to know. Second, as you can see, though it is not a perfect circle I have drawn here, but this is the Bohr model of an atom. In the center is the nucleus, and there are many electrons revolving around the nucleus. The one on the outermost part is the valence shell, and in the inside are the inside shells of course. So the first another thing you need to know is these inner shells are usually unaffected when many atoms come together, but the valence shell is usually affected when many atoms come together. This you will understand what I am trying to say when I proceed further. This is the first diagram here of the energy band theory. In this, as you can see here, on the y-axis is the energy. On the x-axis it is d, which is actually the interatomic spacing between the atoms, not electrons, between the atoms. So first we see a straight line here, two straight lines. This actually represents that when the distance is quite large, the energy interaction between two isolated atoms is almost nil. Both of them are not interacting with each other, and hence there is no energy interaction between those. As we reduce the interatomic spacing between those two atoms, we can see that there is a structure being formed at each atom. As we can see here, the shaded portion, this is actually the energy probability, what we studied in psi, which is the probability of finding the electron in different spaces. Here, when two atoms are being joined together, the probability of finding an electron in that space is actually getting more and more. So here it is this space is increasing as we are decreasing the interatomic distance d. And then we see that there is a big gap in between here. This actually shows the inner shells and the energy is not affected. As I told you before, in the Bohr model of the atom, the inner shells are not affected and the outer shells are affected, which are the valence shells. The inner shells are not affected at any point when these two atoms combine with each other, or not combine exactly, when they are coming together. So we start the diagram above this dotted lines, which shows the inner shell's energy. Then we come to the second diagram. Here we are decreasing the interatomic spacing between the atoms, and then we are drawing another diagram. Now this was the position where those two atoms were quite far away from each other, and when these were brought nearer to each other, this diagram takes shape, and this shows that bands are being formed here. This is one band, this is another band. This is usually known as the conduction band, and this is known as the valence band. And as you all have seen that there is an energy gap, this distance is the energy gap. So I hope you have understood what the conduction band and the valence band is. Now we will go on to classify different materials based on the energy band theory. Here is the classification of materials. First we have insulator, then conductor, then semiconductor. First we will cover insulators. As we saw earlier the energy band theory, here is the conduction band, here is the valence band, and this is the distance as we saw earlier. So in an insulator, as you can see that the distance or the energy gap Eg is 6 electron volts. This is actually quite a lot. We know that electrons are always stored in the valence band. So the electrons have to move from the valence band to the conduction band for any conduction purposes. So it has to cover an energy distance of nearly 6 electron volts, which is quite a lot, and even at very high temperatures the electrons can't gain that much energy to jump to the conduction band, and hence it does not conduct and is known as an insulator. Then we shift to conductors. Here we are seeing that the conduction band and the valence band are overlapping with each other. as you can see this area, this is the overlap area. So any electron which is in the valence band is virtually in the conduction band also. What I am saying is virtually. So you can understand that conduction is very easy and the electrons can move very easily from the valence band to the conduction band even at room temperature, which is nearly 25 degrees Celsius, and here is an overlap. And then we shift to semiconductors. In the semiconductor there is the conduction band, the valence band, and there is a small energy gap Eg, which is nearly 1 electron volts. This energy is actually very small, and at least at normal room temperatures of 25 degrees Celsius, some of the electrons gain enough energy from the valence band to jump to the conduction band, and hence it can conduct. And if the temperature is increased, say 30 degree or 35 degrees Celsius, this energy gap actually reduces and the conduction increases quite fast, and the more and more electrons from valence band to the conduction band start moving. We have shown the semiconductor in the end because we wanted to show the classification of semiconductors. There are mainly two type of semiconductors. First is intrinsic, second is extrinsic. In extrinsic we have two types, the N type and the P type. These are the types of semiconductors.